Hello everyone, welcome back, and this is lecture 18. Today we're going to learn about what is sequential circuit and how to design a sequential circuit. So um, first of all, basically from last lecture we learned about some of the memory element such as latches and most importantly flip-flop. So in this lecture, we will learn how to use the flip-flop to make a sequential circuit. Um, so what is sequential circuit? Um, First of all, sequential circuit is basically it's a state decision-making state transition machine. So the machine itself, the circuit itself, have an internal state that will transit from one state to another state based on what is the input that you provide. Also, from the current state or the current combination of input or end state, you can provide certain output for your sequential circuit. So first of all, in order to understand how to design sequential circuit, we have to understand what is the state transition in our flip-flop. So I will go through a couple examples about state transition of JK flip-flop and D flip-flop today because we have went through the state transition. We have studied how D flip-flop work very well in previous lecture. So today we will learn how the state transition of JK flip-flop is going to work. First, you have the JK flip-flop diagram here. Okay, this is your JK flip-flop. Your JK flip-flop have two input. I would say the two input is going to be AB, and it have the output, right, which is showing the next state. Okay, so you remember it only the output only have two possible outcome, which is going to be either 0 or 1. Okay. So then, because the output have only two possible outcome, either 0 or 1, that means the JK flip-flop only have two possible state, it's either S0 or S1. Okay, so I would say the state S0 is when the output is 0, and the state S1 is when the output is 1. Okay, so from here I can have the something called a state diagram. Okay, so state diagram is a diagram that consisted of a bubble. Okay, actually several bubble showing different state. Each bubble represent for a state of the machine. So for example, we have two possible state, which is S0 and S1. Therefore, we only have two bubble here. Okay, S0 and S1. S0 is when y equals 0, and S1 is when y equals 1. Easy. Okay, then you also have a tool which is called the state table. Okay, so the state table tells you that the state table tell you that what is the present state. Okay, and with a certain input combination, after one clock cycle, what will you have for your next state? Okay, so your state table will basically tell you how your state transit from present state to next state given certain input. Okay, so do you guys remember what is the properties of JK flip-flop? So I will remind you guys here. Properties of JK flip-flop is if you have both J and K equals 0, the value of Q is gonna hold. If you have both J and K equal 1, the value of Q is gonna be flipped in the next clock cycle, of course. If J equal 1 and K equal 0, Q will be outputted as 1, and if j equals 0 and k equal 1, then this value Q right here will become 0. Okay, so technically you can either hard assign the value of Q to be 0 or 1, or you can either flip or hold the value of Q in the next clock cycle. Okay, so first of all, for example, if we started, let's say if we started at the first state right here, which is S0, okay, and you know that the output is 0, if both A and B equals 0, what is going to happen? And you know that if both A and B equals 0, you hold the value, right? It doesn't change. So because you hold the value, the output now go back to its current state. Okay, so that's why you have these arrows that looping back to its all bubble. Okay, so you see right here, you have A and B is 0, so the next state of course is 0. Likewise, when you have A and B both equal to 1, so AB equal to 1 1, in that case you flip the value, right? When you flip the value, you transition S0 to S1. Okay, so you have this state right here. Okay, so on, if you have AB equals 0 0, keep the value, so S1 will S1, right? Okay, okay, so I just went through what happened if AB equal to either 0 0 or 1 1. Okay, if it's 0 0, it go back to its current state. Okay, if it's 1 1, it will go to the other state. There's only two states in the system. Okay, what if it's gonna be either 0 1 or 1 0? I mean, I'm talking about AB. If it's, for example, if your state is S0, okay, so we'll talk about this case. If your state is S0 and your input is AB equals 0 1, now you know that if AB equals 0 1, the next state of Q will be 0. So next state of Q will be 0, which means it will go back to the same place. Okay, so you know that if present state is 0 and AB is 0 1, it go back to the same state. And if AB is 1 0, it will go to the other state, because now you will hard assign this output to be 1. Okay, so just go to another state. So likewise, if you are at state S1 and you input a 0 1, the output of the next clock cycle will become 0. So you go to the other state here, and if you if you are at state S1 and you give the input of 1 0, the output of the next clock cycle will be 1. So that means you will go back to the current state. Okay, so that is the state transition of a JK flip-flop. What I want you to remember is how we have a diagram here, which we will define later how to use it. But this diagram is called a state diagram. It consists of the state bubble defining your state, and the decision path, which show you the transition to another state or back to its current state based on certain input. Okay, now we will repeat this exercise on T flip-flop. So T flip-flop, which is a lot more simpler than JK flip-flop, because technically, if you remember, T flip-flop, basically we just connect the J and the K together and supply a single input. Okay, so likewise, output only have two possible outcomes, 0 or 1, so we only have two possible state, and we can make a state diagram, right? Of course, we can write down the state table too. So do you remember the properties of your T flip-flop? If you, okay, so the property of T flip-flop, basically if A or if T, if your input equal 0, it will hold. If your input is equal 1, it will flip, okay? 0, hold, 1, flip. Piece of cake. Okay, so that means if I'm at S0 here and my input is 0, I will hold the state. I will go back to the same state. So likewise, if I'm at S1, so if I'm at S0 and my input is A1, then I will go to the next state. I will go to the next state here, okay, because flip. So if I'm at S1 and my input is 0, go back to current state. And if my input is 1, then I'll go to the other state. Okay, so that is the state transition of T flip-flop. So go back to the basic here. So in order to design a sequential circuit, you guys need to basically analyze your specification. Okay, you have to analyze this clock sequential circuit. So the analysis means you have to understand what will happen to the circuit under a given condition in the next clock cycle. Of course, it's a clock circuit. So in order to perform the analysis, so in this lecture we will study about some basic tools that you need. So you need to use to basically analyze your circuit or analyze your state transition in your state machine. State machine is basically another term for your sequential circuit, because your sequential circuit will transition between state and another state. So those two is gonna be your state equation, your state table, your state diagram, and the flip-flop input equations. So first of all, we will go through the state equations. So this circuit here, if you have your textbook, it will be in my textbook is the figure 5.15. Okay, an example of a sequential circuit. So if you look at this, I'm sorry, I just trying to crop the image, but this is just A and B. It's not A minus or B minus, so excuse me on that. But if you look at this circuit diagram, okay, all right, you can see that, okay, now it has some flip-flop here, right? This has some flip-flop here, and it has some input combination. I mean, it has some combinational circuit here, right? And also the output is provided by Y is provided by some combinational circuit with the input of the current state, okay, and also the input of the system X. Okay, so now what I want you to do, you can pause this if you want. I want you to write a set of equations that describe the next state of A and B based on the previous state of A and B. Okay, so I will start going here. Okay, that means I will describe next state to be T plus 1, and if you have next state to be T plus 1, the previous state will be T, right? So you can have, when you write down the state equation, the next state will be on the right hand side, I mean the left hand side, and the previous state will be on the right hand side. So let's start writing it. So for A here, if you look at A, A is basically A for the next state of A coming from this D flip-flop, right? Okay, so the next state of A coming from this D flip-flop, and now you have next state is A t plus 1 here, and AT will be AT, right? AT plus 1 will be in here actually, sorry. AT plus 1 it will be in right here because the next state will be pushed here. So AT plus 1 is here, AT will be here, okay? If AT is here, then you can write an equation based on this combinational circuit. So you see that you have two terms, right? You have two terms going to an OR gate, and one term is A and X. The other term is B and X. Okay, so that's why you have the equation AX or BX. Okay, so now we go to BT plus 1. So BT plus 1 is simpler. Of course, you have the access right here. So first of all, you have the first input of the AND gate is A0, okay, and the second input is X. So of course, the equation will be A0 X, okay. And why I kind of skip the T's when I talk about that, because you can actually omit the T for the convenience. Okay, mathematically you can put the T here, but because since you all know the previous day will be just on like AT, XT, something like that, so you can omit the T for your convenience. And also finally you can write your equation of the output Y just based on this combinational circuit. So you can see Y will be equal to, there's an AND gate here, there's an OR gate, so it will be A or B, then AND with a X0. Okay, so A or B and with an X0. Okay, now we will talk about the state table of the previous circuit. So from the state equation, so I'm just gonna write down here, right? Of the state equation and the output equation, you can construct a state table. Okay, a state table will include a present state. So we have, as we see here, we have two D flip-flop, right? We have two D flip-flop in here, and each D flip-flop will have, you know, like an output. So this A, each D flip-flop will have its own state. So A here represent for the first D flip-flop A, and it will output, you know, it will output either a 0 or 1. And also the second D flip-flop will output a 0 or 1, so you can have the state B of the other D flip-flop here. When I say A and B, of course I was talking about the the output or the state of the D flip-flop. So you know that each D flip-flop have two states, right? Either 0 or 1. So when you combine two D flip-flop together, you actually have 4 states. Okay, if you see here, the combination of 0 and 1 of A and B, I have 4 different combinations, right? That means I can have 4 states come out of this 2D flip-flop. I also have an input X, right? I also have an input X. So the input X, so it's either 0 or 1, okay? So I can just write down, so basically what I write down in here is for the present state 0, 0, what happened to the next state in the output when my input is either 0 or 1, okay? Then I will examine the other state, 0, 1, with one of my possible input combination, and so on to the last present state, which is 1, 1. Okay, so how can you fill in this table next state and output? If you need some time, please pause your video, take a few minutes to use this state equation, fill out this table, then we can go back and compare. Okay, so here is your answer. So you have the, of course, so you can fill off the state equation. So you will have what happened in the next state, right? And also what happened in the output. Okay. When you write down the output, you have to remember that the output coming from the present state, not from the next state. Remember that I didn't write a t plus 1 or b t plus 1. It's a, b. So it's the present state, okay? Okay, so before we start, I'm gonna talk about the second form of the state table. So differently from the first form, when you have present state input, next state output, in this state table, you only have present state and next state, and you can have another column for output. You can make a sub column for different input combination or different input. Then you can fill your state table accordingly. So providing the state table, you can generate a state diagram. Okay, so first I want to talk about the state diagram, which is first I want to talk about the state diagram, which is on the floor of the state bubble. Okay, so the first state bubble, because this state machine have 4 different states, so it have 4 different state bubble. Each state bubble represent for one state with a certain combination of A and B. So S0 is AB equals 0, 0, S1 is AB equals 0, 1, S2 is AB equal 1, 0, and S3 is AB equal 1, 1. So let's examine this state table and we can figure out how to complete the state diagram. So when you have at state S0, when input is 0, it loop back to is all S0, right? But when input is 1, it go to state S1. So when input is 1, it go to state S1. But you can also, because of a certain combination of the present state and the input, you can use some output also. So the output yielding for these two paths are both y equals 0. So when you see the notation flash and a second number after the flash, usually that second number represent the represent the output of the system. So now we're at state S1, right? So at state S1, the current when x equals 0, it go back to state S0. When x equal 1, it will go to state S3. So if state S1, if so x equals 0, go to S0. If x equal 1, go to state S3. Okay, so now we will examine state S3. If we're at state S3, which is here, if x equals 0, it will go back to S0. But if x equal 1, it will go to state S2. Okay, and when x equal and at state S2, when x equals 0, it will go back to state S0. But if x equal 1, it will loop back to state S2. Okay, and I will have all of the output accordingly along the decision path. So instead of writing everything so long in this form, you can actually, because you know exactly you have only one type input, or you have some input combination, and you know your output, you have your output right here. So another way is you can skip you can skip the X and the Y, and you can write your decision path like this. The first number represent for the input, and the number after the flash sign representing for the output. Okay, so the next tool we're going to talk about is the flip-flop input equation. Okay. Okay, so when you see in here, this is basically just the truth table. Basically, this is the state table when I have present state, input, and next state, right? But what you see is basically I add another column for DFF, which is D flip-flop input, since the next state of the D flip-flop the D flip-flop is actually the input of the D flip-flop, right? Because next day after one clock cycle, the data get passed through the from D to Q. So next day of D flip-flop is the input of the D flip-flop. Therefore, you can actually copy the exact column of the next day for the D flip-flop inputs column. Okay. So this one, the same. So now I simplify down this table into a present state input and DFF inputs. So now I can actually treat this table like a normal truth table, okay, with present state and input A, B, and X to be input of the truth table, and the DFF inputs column DA and DB to be the output. So now you have a truth table, right? So you can use this truth table. Either you can use Boolean algebra, or you can use K-map to come up with and simplify your Boolean expression for DA and DB. So first of all, I will try to provide a Boolean expression for DA. First, I will try to make a K-map for DA. So from this truth table right here, I can yield a K-map. Okay, now we're gonna start grouping. So we will group this group and this group right here, and we know this group will yield us AX, while this group will yield us BX. So the equation for DA will be DA equal AX plus BX. Likewise, we can do the same thing with the DB column. So we can make the K-map for DB. So this is the K-map for DB. And how can we do the grouping? Right here. Okay, we start grouping it and provide the terms. So now we have the DB equal A naught X. So now we can have the D flip-flop input equation set is DA equal AX plus BX, DB equal A naught X. Okay. Finally, we started with the circuit, right? We have all of the element, but actually, if you remember, we have the state table, right? So from the state table, we can have the state diagram. From the state diagram, state table, state diagram, that one you can go back and forth. Then from those elements, you can make the D flip-flop inputs equation. So from that D flip-flop input equation, you can construct your combinational circuit outside of your D flip-flop. So because first of all, because you have 4 different states, right? You have 4 different states, and you use D flip-flop, so you will use two. You will use 2 D flip-flop in here. Okay. Then you will use your first D flip-flop input equation for the first D flip-flop, which is DA. So you use that input equation to construct the first combinational circuit. Okay. Then you use the second equation to construct the second combinational circuit, and also you have the output equation, right? You can use that output equation to construct the combinational circuit to yield the output. Okay. So how can we come up with a procedure for designing a sequential circuit? So first, you can design your state diagram. Okay, and this state diagram is based on a specification someone give you that they want that circuit, how the circuit to perform. So you can make some state diagram like this. Okay, you have to create a state table from the state diagram. Um, but actually sometimes you can do step 2 first and you do step 1. So step 2 and 1 is up to how you decide, but easy way, because visually and graphically it's easier to make the state diagram, so I would preferably go with the state diagram first, and from that you can make a state table. From the state table you need to derive the equation for input of the D flip-flop. So let's say, input of your flip-flops, because we can actually use J, K, and T also. So for example, if you use D flip-flop, you need to come up with what is the equation for the input D, and finally you make the circuit. Okay, so we're gonna start learning about each different element in here. The state diagram. So when given an initial constraint for your sequential circuit, you must think about like a different state that you need to put in your circuit, uh, and that the circuit is gonna be in the given time, and how the state is gonna be transitioned between one and another based on your inputs. So the state diagram is kind of like a map, like a decision making map, actually map. Uh, so from that diagram you can see with what input your machine can go from one state to another state, so you can navigate the decision making using the diagram. So in the diagram, the state diagram, you have two keys element, which is the state bubbles, that circle thing, and the decision path. So this is one of the example. For example, if you have 4 different states here, so each of this circle here is a state bubble. Okay, you can make some kind of path that go transition from one state to another state. Okay, so let's say you can have different input combination. Yeah, so sometimes you have 2 input, but some decision path, for example, let's say in this path, B can actually be don't care also, so you can use both input. Sometimes you can don't care one of 2 input, for example, but the main point is you have to know like for what type of input your state will change from one state to another state. So the bubble is represent the state. This arrow is the decision path. Sometimes you can actually have one state, for example, one state, and you don't need any input. That means like A equal don't care, B equal don't care. You don't need any input. Immediately after one clock cycle, it just go to the next path. Okay, so that is like the next state. That is if you don't give it any condition. That's what it means. So each state bubble can be encoded to a binary value supplied by, let's say, a set of D flip-flop, but also you can use J, K, or T flip-flop for this case. Okay, basically the number of state in the diagram will indicate how many flip-flop that you need. So if you have 4 state, you need 2 flip-flop, because it's 4 state will be 2 to the 2, right? 4 equal 2 to the 2, so you need 2 D flip-flop. So that n number is your number of flip-flop that you need. You can have if you have 3 state, sometimes you have a 3-state system, then you still need 2 flip-flop. So the number of state have to be equal or smaller than this number. Okay. The next element is the state table. So the state table, we went through the example, we know how it works. So it's just a tabulated form of how one state transition to another state. So usually you have current state, input, next state. Sometimes you have an output column also, depending on your system. Some system doesn't require to have an output. Some system will give you an output, so it depends on different type of system. So you can see usually it just show you with a certain combination of current state and input what will your next state will be. Okay. And finally, you need to learn how to derive. You need to derive your flip-flop input equation. So from the state table, so you have to use an equation for input of each flip-flop. You can obtain it. Okay. So in the case of D flip-flop, use the value of next state as the columns for value of input D. You can construct the truth table, okay, using the input. You can construct a truth table using inputs and the current state as inputs of that truth table, and using the values of input of the flip-flop, such as like D input value as output of your truth table. And finally, you can use either K-map or Boolean algebra to simplify your flip-flop input equations. And at the end, once you have your equation, you can construct your circuit. So if you use D flip-flop equation, if you use D flip-flop, right, you can use the D flip-flop equation that you obtain to create a combination circuit that match. So for example, you have 4 state, you can use 2 D flip-flop here. You have some type output. You can construct the combinational logic. Okay, this is based on the flip-flop input equation or the flip-flop input equation. Then let's say you have some so you sometimes you actually feedback. Actually, you always feedback the output. This is output of the D flip-flop. I would say this is not output of the circuit, because output of the circuit, it depends on your criteria. You can make, sometimes you can accept the output of the D flip-flop as the output of the circuit, but sometimes you can actually use a combinational circuit to combine input and output of D flip-flop to make your own different type output. So we can have so the design process of sequential circuit. So basically, let's go through an example. Let's say if you have if you want to design a circuit that keep track of a sequential input of 1-bit binary number. So let's say if I have a machine right here, okay, and my input is just either 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, something like that. If an odd number of ones has been placed into the circuit, then output is 1. If an even number of ones have been placed into the circuit, and let's have an output of 0, that means our state machine right here have to be able to keep track of 2 state, which is odd state and even state. Okay, so we can have a state diagram. Let's say even state and odd state. Okay, so now you can, let's say if it's at even state and the next input is 0, that means the total count of ones doesn't change, right? So it go back to its original state. But if the input now become 1, that means an even number become an odd number, so it go back to the next state. So if input equals 0, the total count doesn't change, so odd come back to odd. But input is 1, then odd become even, so it go back here. So now you complete your state diagram. So now you think about how many flip-flop do you need. You have 2 state, so 1 flip-flop. So you can make a state table. So you can easily construct a state table. Okay. So you can have the current state and giving it the next state. If you need to pause and solve this yourself, take your time. But I'm just gonna go through this one quickly. So based on this state diagram, you can construct a table. And finally, you have to derive your equation. So you have the first equation is your d0 equal q0 0 and input, or q0 and input not. So you can use an XOR for this, right? So now you can make a circuit using 1D flip-flop. Okay, you can provide an XOR, some input, feedback with the current state, which is the Q0 output. Okay, so adding combinational logic to your circuit output. So circuit combinational logic can be added to the output of the circuit to get different behavior out of your circuit. So what do you want to change in your design process to accommodate this new logic? So for example, if you have your state diagram, right? And remember this flash. So sometimes you can easily describe the transition between state, but also you can make an output, right? You can make an output out of it. So this extra value is basically the output that is provided by two things. What's the present state? What is the input provided? So you can easily have some kind of like a state table. You can use that as a truth table, and you can derive your equation and construct your circuit. So you can make an extra combinational circuit right here, and remember our first example when I have the Y equation. You can do the same thing, construct your combinational logic as input. Okay, so next we will go through how can we, so we have been dealing with D flip-flop a lot. So next we will go through how to make a sequential circuit with other type flip-flop, which is JK flip-flop and T flip-flop. Okay, so for D flip-flop, we can use that as memory storage, shift registers. But for JK or T, is have other function. You can use it for something like counter or circuit that you want the output to toggle back and forth. Okay, so we will start with learning how to design a sequential circuit for JK flip-flop. Okay, so let's say we are given this state diagram in here. Okay, so first of all, what you can do is you can fill out your state equation, your state table, right? That means you can have your present state, your next state. You can fill out all of the combination of input and present state. Then according to this map, you can fill out your next state, okay? But here's the next question that I will ask you, and you can pause for a few seconds to look back to previous lecture. What is the properties of your JK flip-flop? That means if you give a combination of J and K, what will be the next state for the next state for output of JK flip-flop? So let's pause for a few seconds there. Okay, so you can all see that the next state, so when you have both J and K equal 0, you hold the value. If you have both J and K equal 1, you flip. If you have J equal 0, K equal 1, then your next state equals 0, and if you have J equal 1, K equal 0, next state equal 1. So now from there, you can easily fill out the rest of this table. Okay, so for example, I will go walk through a few examples here if you have any question. So for A, let's say A, so present state is 0, next state is 0, so hold, right? So 0, 0, for example. But in here, A, 0, but A next state become 1, so flip, so become 1, 1. For example here, present state is 0, next day is 1 is 1. Okay, so you can either use 0, 0, or you can either flip, which is 1, 1, or you can also do 1, 0. Okay, this is one of the choice. And likewise in here, so 1 become 1, so either you can how can I say this, 1, 1, either you can hold, which is 0, 0, or you can make it 1, 0. Yeah, so 1, 0, output always is 0. Okay, so actually if you have a different answer from this, that's still acceptable. Okay, like for JK flip-flop, the answer won't be so fixed. Next is, now you have the state table with the JK input row columns on it. You need to find the JK flip-flop input equations. So from the previous one, the table, you can make a K-map for first JA. Okay, so you can fill out the K-map for JA and you can start grouping. So you can obviously see this group right here. The term is gonna be B. So you have the equation JA equal B. Now you move on to work on KA. So fill in the K-map and you can start grouping. Okay, so you can have the equation KA equal B x naught. Now you move on B, so you work on JB. Okay, start grouping and you can see the group is going to be that Pac-Man right here. Okay, it will give you an x naught. So JB equal x naught. And finally, you can have KA. Okay, you're gonna find, you're gonna have a K-map for KB. Okay, so you can have this group here and this Pac-Man group here. Okay, so that it means two terms. So you have x naught A and A x naught. So your equation will be KB equal AX naught plus AX naught plus X naught, A naught X, and this equation will equal to XOR, right? So you have A XOR X. And finally, you can put everything together in your final circuit implementation. So similarly to JK flip-flop, you can do the same thing with T flip-flop. Okay, so given a state diagram like this, and remember previously I showed you like on the decision path you can have a flash sign and the second number will be the output, right? You can actually do the same thing in the state table too. In the state bubble too. So if you have a flash sign right here and you can have the output, the only thing you have to remember is for this type of state machine, the output is only depending on the current state. The output will not be depending on the input. Okay, it depends on the current state. So you can easily make from this state diagram, my laser pointer. From this state diagram in here, you can easily make a state table with present state, input, and you can have next state and output, right? But let's take a couple minutes, or let's pause this video for 1 minute to go back to see what is the properties of T flip-flop. Okay, so now you know that T flip-flop is basically same thing with JK flip-flop, but you don't have J different from K. You just J and K always equal to each other. So if T equal to 0, you hold. If T equals to 1, you flip. So you can easily derive what's the input TA and TB is gonna be. So for example, let's go to this one. So if I have 0 and next day is 0, then of course right here will be hold, right? Hold is 0. But if I have 0 and next day is 1, then it will be 1 because I need to flip. So see, 1 flip, 0 hold. Okay, after you have this table, TA and TB, okay, so similar to other case, you will take out this 2 column next day and output. You keep the present state, the input, and the T flip-flop for your truth table. Okay, in this case, I just put the output here because I will use that for later. But what you can do is now you can make K-map. You can make K-map for TA. Okay, so make K-map for TA using this table. And you started grouping. So you start grouping and you have TA equal BX. Okay, now you start grouping for TB. Okay, you start grouping for TB and you can group this big group here. And you can have TB equal X. And finally, you can make K-map for Y. So you make a K-map for Y. You see, I actually I eliminate the X variable in here because output Y is independent with input X. So I don't need to put X in here. I just need to use A and B. But in this case, I use K-map, but actually if you look into the truth table, it's a lot easier just to use the mean terms from the truth table instead of using K-map. But anyway, from this, you can have the equation to be Y equal AB. Okay, and from all of this, you can make your sequential circuit of the T flip-flop. Okay, so now we learn about Mealy machine and Moore machines, finite state machine. So what's the difference between two? So we learned about like basically a state machine or sequential circuit. It can have an input, it has some internal state providing from the flip-flops, and it will have the output, right? So the Moore machine, okay, the Moore machine, the flow is like this. So for the Moore machine, the output logic is only based on flip-flop. So the previous example of the T flip-flop sequential circuit is actually a Moore machine. So output is only based on the state of the flip-flop. Okay. But Mealy machine, okay, Mealy machine is the output is actually depending on both the state of the flip-flop and the input. Okay, so that's the difference between the Moore and the Mealy machine. Okay, we have a couple slides left. So combinational circuit simplification. So this is quite easy, but we have done all of this using a K-map so far. You can try to minimize your equation, so you can trying to make your circuit more simplified. You can use some state table like this, but remember, sometimes you don't use all of the state that you need. Sometimes, let's say you use 2D flip-flop, you only have 3 states. So the extra state right here, you can use it as don't care, right? So instead of using Boolean algebra, you can actually use some K-map method, right? And if you use K-map, you can try to simplify your equation even more. Yeah, so in that way you can have a more simple equation. So key to remember is trying to combine all of the method that you have, include don't care and everything to simplify your circuit as much as possible. Also, there's a technique called state minimization. So sometimes you build all of your state diagram, but you figure out some state is not really necessary, so you can start removing it. Okay. So if two states both have decision paths that lead to them to the same state uh, within the diagram, have the decision path that lead to them that require the same input, and all decision path for the two states have the same desired output going to each state, one of them can be eliminated. So you can see, for example, in this map right here, yeah, the S4, the S3 and the S4. So S3 and S4 have matching decision path. Okay, so you can eliminate one of them. So you can see that S3 both have a decision path going to S5 and S1. This one also going to S5 and S1. So you can eliminate this one and yeah, move the other link to here. So you don't need on 6 state, you can minimize one of the state.